Have you ever been driving and came across these giant towers and thought, what in the heck are they? Well, most likely they were transmission towers. And in today's video, I'm going to go over exactly what they are, how they operate, and what role they play in Australia's power sector. Hi guys, Jack here, back for the fourth video in the Beginner's Guide to the Australian Power Sector series. And today, we're going to be delving into the world of transmission. Now, as always, the goal of this series is to provide you guys with the background knowledge about all things power in Australia. So by the end of the series, you'll be able to walk away and have the contextual knowledge required so that you feel comfortable talking about the power sector in either a public or professional environment. As I mentioned before, this is the fourth video in this series. So once this video is finished, feel free to roll back to my other videos where I talk about the power sector overview, as well as all things generation. So without further ado, I'm going to jump into my desktop and let's get into the wondrous world of transmission. Alrighty, so as we can see here in our little diagram, transmission sits kind of in the second place in terms of roles in the Australian power sector, essentially serving to provide long distance transport of electricity. So that's transmission in a nutshell. But in today's video, we're going to cover four key areas. So the first being Australia's transmission assets, so what enables us to actually transmit power in the Australian power sector. The second is going to be what actually classifies a transmission line and what sort of structure they're built with. The third point is actually how transmission interconnects with the rest of the network, kind of like the diagram I was showing before, as it sits in the second. How does it connect to the first and the third parts of the network? And the fourth being really looking at a future outlook, which is essentially looking at the current problems and some potential future solutions. So let's get right into it. So the first thing we're going to have a quick look at is, what does transmission actually look like in Australia? To begin figuring that out, we're going to start with the AEMO transmission map. So if you're unfamiliar with who AEMO are, they are essentially the market operator. If you want any further details, I recommend going back to my power sector overview video, but essentially they're the market operator. So as you can see from this map here, the little blood vessels are what is actually the transmission lines. So as I also detailed in that power sector overview video, there are two separate networks in Australia. We have the NEM and the WEM. So the NEM in Australia actually has around 40,000 kilometers of transmission network, whereas the WEM is a little bit smaller. We have 7,750 kilometers. And you may be wondering, what difference is the colors here? So the color is actually, I guess, significant of the voltages. So depending on the color and a map you'll see in a moment, the color signifies different levels of voltages. So what I'm actually going to do now is jump onto AEMO's website and look at this image live. So I'll be back in a second. Alrighty, so we are now on the AEMO website. So I'll leave a link to this in the description of this video, but what I wanted to show real quick is AEMO's effort to actually visualize the transmission network for you guys. So if you go up in the top left and click electricity network, transmission infrastructure, and let's first look at transmission lines. So you guys will see before the capture I took is essentially the static of this. So you can see the NEM's transmission lines ranging from Cairns down to Brisbane, through Sydney, Melbourne, a link to Tasmania, and then through to Adelaide, and then the WEM, which is a bit over the other side through Perth and a bit up at Geraldton. So if we zoom in a bit on this, you guys can see there's actually a lot of different colors. So you can use the legend on the left there. So as you can see, different states use different transmission voltages. So up by Cairns, we can see we've got a bit of brown, which is 66. We've got some pink, which is 275. And then we've got some red, which is 132. So I'm pretty sure Queensland uses the same transmission voltages as SA, being 275, 132, and 66. And then if we go down to Sydney, for example, they use a bit different. So they use some 500 kV lines going from their big load centers. They also use 330 through the top here. So going back down to Victoria, who use 220 kV transmission lines, which is again a bit different. We've got a high voltage DC 330 kV link to Tasmania, which I will talk about later. And then, as I said before, Adelaide uses the same as Queensland. So we've got 275, 132 and 66 mostly in the metro areas. All right, so going over to the WEM, we have a lot of different transmission lines here. So I'm pretty sure this is pink, so 275. We've got a bit of red. We've got a few orange ones as well. So as you can kind of take away from this, we have a very big different range of transmission lines in Australia. So if I go back over here on the left and click transmission substations, which I will speak about later, you guys can see there are so many different subs because obviously there's so many people that want to connect and interface with the network. So therefore there has to be a substation to convert down. So kind of a big picture here, but as I said, I'll leave this link in the description down below. So if you guys want to have a play around with it and have a look what's in your area, feel free to do so. But for now, let's jump back into the presentation. All right, so now that we have a good visual of the transmission infrastructure in Australia, we're going to move on to classify what exactly is a transmission line. So there are 3 different operational criteria that we can actually use to classify a transmission line. The first being that it's used to transmit power over long distances. The second is that we use it to transmit large amounts of power. And the third being that we operate those transmission lines at high voltages. So the purpose or kind of core goal of transmission is being able to transmit power long distances from the place of power generation to the load centers. So things such as capital cities and things like that, where we don't always have those big generators right next to them. So in order to get them power, we have to transmit power that long distance, which is exactly where transmission comes in. And now you may be thinking, why must we use high voltages? Obviously high voltages, it's much more a safety risk. We have to maintain much higher clearances for things like this, but it really boils down to long distances result in higher power losses, which equals a high cost, which as I've noted here is bad. Nobody wants to pay more than they have to for a certain thing. So as the core purpose is revolving around those long distances, what we have to do is minimize our losses. So as you can see by these few equations here, power loss is essentially equal to current squared times by R, where R is resistance and I is current. So as the current is a squared variable, we have to really minimize this in order to minimize our losses. Moving to our power equation, which is power in watts is equal to voltage times current. In order to keep our constant or large power, we have to maintain a balance between voltage and current. So either one has to be higher, one has to be low, or they can both be medium. So as we want to minimize current, we have to maximize voltage to keep that large level of power being transmitted on our transmission line, which is also one of our key operational criteria. So to conclude, essentially, we keep our voltages high to keep our current low to minimize power losses over those long distances. And you may also be wondering, how do we actually step up and step down these voltages and currents? And that's through a power transformer, which I covered a bit in the last video in the switch yards, but I will have a look at later in this video. So let's move on into how these transmission lines are actually structured. So there are 4 key components of transmission lines. Number 1 being the structure, number 2 being the conductors, number 3 being the insulators, and number 4 being a path to earth. So looking at structure, the primary purpose of structure is to provide mechanical support to the conductors. So this structure must abide by clearance requirements. So with reference to that diagram on the right there, this is why essentially transmission towers need to be so high, because they have to maintain distances between the top power line and the ground, because power can quite literally arc to the ground or arc to a truck driving on a road where a transmission line is across if the clearance is breached. So transmission towers are kept generally pretty high in order to kind of maintain that. Now, these towers are mostly built out of steel and can take some different configurations. So they can either be built in kind of a lattice, as is shown by the diagram here, or they can be built on general Stobie poles. It depends generally depends state by state. Alright, so key component 2 being conductors. Conductors are essentially the actual power lines, and they provide means for power transfer. Now, you can see by the diagram here, there's 3 different wires. That is for the 3 different phases of the actual power. Now, each of these wires is actually rated to a certain power capacity, which essentially defines how much power a certain circuit of transmission line can take on. The third key component of transmission lines is our insulators. So they essentially allow our conductors to actually hang on the structures without being earthed. So conductors are normally made out of porcelain, and they will quite literally hang on clamps off of the, kind of as you can see there, the little triangle outriggers of your power structure, and then they hang down, and then the transmission line is clamped to it. So these insulators have little ribs on them, which essentially increase the resistance to flow through the structure rather than along the line. So as you guys may know from your theoretical studies, power will always take the path of least resistance. So by adding those ribs, the distance to ground is greater than the distance along the line. So as the power line is the path of least resistance, it will still follow it. And again, these are rated to certain operating voltages, characterized by the amount of rings actually on the insulators. So depending how high the voltages are, there'll be more ribs on those insulators, because the higher voltages, the more resistance you need for the fault current, etc, etc. Now, the fourth key component is the earthing path. So as I said before about the insulators preventing the power going to earth while enabling structure, the earthing path essentially allows fault current a safe path to ground. Now, these faults could be a line fault, like a tree hitting a line, something like that, as well as lightning strikes, because you think about these big structures, they're essentially a big lightning rod. So if it gets struck by lightning, the line needs a way to go to ground safely. Alright, so we've covered transmission lines. Now we want to know, how do these transmission lines actually connect to the rest of the network? So this is actually through what we call a transmission substation. Now, transmission substations serve 2 purposes. Purpose 1 is to provide connection points between generators and the network. And purpose 2 is to provide connection points between the transmission network and the distribution network. Now, this makes pretty good sense if we take back to that original diagram. So as we can see here, transmission sits between generation and distribution. So the purpose of these transmission substation is to provide that link exactly. So with reference to the figure on the right, we use a range of different infrastructure in this substation. Probably the main bit of infrastructure is what we call a power transformer, which essentially transforms our transmission level voltage, which depending what state you're in can be 275, 500,000 volts, etc., down to distribution level voltage, which again, depending on what state you're in, can be 66, 33, 11, 24, 36. Again, it very depends on what state you're in. Other key devices in transmission substations are what we call protection devices. So as you can see on the diagram, we have some circuit breakers, which essentially act to protect our infrastructure in the event of a fault. So they're designed to automatically trip if certain conditions are met. And another protection device, being the line disconnectors, act as essentially manual switching points. So say certain maintenance had to be carried out in that transmission substation, some lineys or some subconstruct crew could go in there and switch it, do the work, and then switch it back on. Another bit of key infrastructure here is what we call secondary metering. So these involve things such as voltage and current transformers, which essentially, through different turns and windings, tap the current down from operating current down to levels that can be sensed by relays and things like that, and they can be fed to communication and protection devices such as the circuit breakers. So there's also things like the gantry and bus bars that essentially allow us to configure the transmission lines to maintain our clearance levels and pass it through our other key infrastructure. All right, so moving on, let's have a look at who actually operates the transmission lines. So funnily enough, transmission lines are actually operated by transmission network service providers, or abbreviated to TNSPs. So the TNSPs are the operators of the high voltage electricity transmission networks, and they're responsible for essentially planning and the development of the network in accordance with the reliability and security standards set by the AEMC, or the Australian Electricity Market Commission. who essentially make the rules. So each state has a different TNSP. So in South Australia, our TNSP is Electranet. In Queensland, the TNSP is Powerlink. In New South Wales and the ACT, it's Transgrid. Victoria, it's AusNet Services. Tasmania, it's Tas Network. So that makes up the entire NEM, being the diagram on the right there. And then in Western Australia, or in the WEM, Western Power is responsible for the transmission network. So in terms of regulation, all TNSPs participate in the AER's revenue proposal process. So again, the AER is the Australian Electricity Regulator. So how that works is essentially every 5 years they make submissions, which are then used to set the maximum allowable revenue, which is essentially how much of the electricity bill they can claim for their portion of their services. All right, so to finish this video off, let's look at what the current problems are in the transmission network and what's actually being done right now to fix them. So currently in their transmission space, I'd like to highlight two key problems. So the first problem is the weakened system stability. So as you guys all know, the government is very set on meeting this 2050 net zero goal. And because of that, we've seen a significant uptake in renewable resource and probably an increased reliance on them going forward, which has resulted in phasing out our traditional rotational generation. So since the start of the Australian power grid, this rotational generation has allowed the market operators and the transmission network to therefore increase and ramp up and ramp down as required to meet different load profiles. So as this rotational generation is being phased out, the transmission networks have reduced capacity to both ramp up and ramp down our firm generation to manage load profiles, which weakens system stability because our frequency swings up and down and our voltage swings up and down depending on our supply and demand balance. And being able to maintain that is one of the TNSP's kind of primary roles. So this is a bit of a problem at the moment, and it's something that the TNSPs will have to manage going forward. So the second problem I want to have a look at is our transmission line capacity issues. Now, as I said before, we've seen an exponential rise in renewable energy sources and particularly trying to connect to the grid. And while this is all well and good, everyone's getting away from fossil fuels, etc. It's all very nice. What it's resulted in the transmission space is a lot of these transmission lines reaching their maximum capacity. So as I explained earlier when I was going over transmission lines, each line is actually rated to a certain power rating. And when that power rating is getting to its peak, meaning all the power pushed into it, it can't take any more. Think about like a full water bottle, for example. That power just continues to spill and the TNSPs can't have that. So say the sun's shining and everyone wants to generate solar into the grid. If that line can't handle it, we've got to curtail those resources. So essentially say, stop, you can't generate anymore, shut your plant down, which isn't what we want when we invest all money into those renewable infrastructure. So as reliance on these renewables increase, the burden on transmission to transmit this significant renewable farms to load centers will increase. So the transmission networks have a significant problem where they've got so many people wanting to connect, but they don't have the capacity in their lines to, take on those connections. So we're at a bit of a crossroads here. All right, so let's look at the current and future solutions to those problems. So in the case of our weakened system stability, Australia's turned to what we call grid batteries. Now, I touched on batteries a bit in my last video on generation, so if you want a bit more of a background, feel free to jump back to that one. But essentially what batteries do is they charge in periods where we have excess renewables and discharge in periods where essentially the network needs them. So in this case, we need renewable solutions to provide inertia, fast frequency, and dynamic voltage control. Now, Australia have turned towards these kind of grid batteries as a solution to this, because they can essentially supply those short bursts of these services to support the grid through periods of supply and demand imbalance. And as we can see by that figure on the top right, Australia has really adopted this. So the y-axis there is the installed capacity and speculative installed capacity due to current ongoing projects, for example, through to 2026. So as we can see, we've nearly got 7,000 megawatts of installed capacity of batteries in the NEM, which is pretty awesome. So this is a big solution that's being implemented to, amend this weakened system stability, and it's going to be a big part of the energy transition moving forward. So our second issue was transmission line capacity issues, which Australia has moved to solve through more interconnectors and transmission lines. So as I spoke about in the problem section, we essentially need more grid connected capacity to connect our renewables. And Australia has moved to permit construction of several significant transmission line projects across the NEM. So I've included two examples here, one being the Marinus Link and two being the Project Energy Connect. So the left figure here is the Marinus Link, which is essentially, there's already one interconnector that flows across the Bass Strait, but the second interconnector they are proposing to build with this Marinus Link. So it's a HVDC link, so it's high voltage direct current link. DC, AC, different things. But essentially what it provides for the transmission network is another way to get Tasmania's very rich hydropower resource across the Bass Strait and toward Melbourne and Sydney load centres, which is very important as we've been restricted in the past with only that one line as to how much we can take. But say Tasmania's well in their means for their capacity, being able to transmit all that energy toward Melbourne and Sydney load centres in the future will be powerful. So this is a great project. A second project is Project Energy Connect. So a bit of background, SA has two current interconnectors, one HVDC that goes through to Mildura, and an AC interconnector with Victoria that goes to Melbourne. So the goal of Project Energy Connect is to interconnect the states of South Australia and New South Wales with a line from Robertstown through to Wagga Wagga, while also interconnecting Victoria through a Redcliffs path. What this essentially provides is additional chance for renewable resources to be connected, but also an enhancement to the state's reliability as it's providing another connection to the NEM. So overall, although the problems we talked about were rather significant, Australia and the companies have taken large steps to implement both solutions in regards to both batteries and more interconnectors to aid in the energy transition. And it's been pretty awesome to see over the past 5 years, everyone band together and get on this kind of train. So yeah, it's been awesome. Alrighty, so we're at the end. A quick overview. So as I said before, Australia's transmission network is nearly 50,000 kilometers of transmission lines. However, the transmission infrastructure is not only lines, we have to have transmission substations to allow those connections to both generation and the distribution network. This transmission infrastructure is operated by what we call TNSPs, which is essentially the company responsible for both operating and augmenting the transmission network. And moving forward, as I talked about with those problems and solutions, I think the key here for our future is to continue to develop solutions that involve more renewable technologies, because that's the real key that's going to help us exponentially increase through the energy transition. So that concludes today's episode on power transmission in Australia's power sector. Next week, we will be talking on distribution, essentially how power is taken from those transmission substations and converted down to voltages that can be actually supplied to your house. And for any further information on anything I spoke about today, make sure to check out these references for further detail if you're curious. But for now guys, I hope you enjoyed that video. If you did, let me know. Otherwise, I will see you next week. Have a good one guys. Thank you so much for watching that video. If you enjoyed it and want to see a similar video on the channel, click right here to see the next video in the playlist. Otherwise, for the latest upload to the channel, click right here. As always, it's a great day to have a great day, and I'll catch you in the next one.